GPS transmission. The GPS Global Positioning System satellites are approximately 5.18 meters across and transmit two low-power signals, one of which is at 1575.42 MHz in the UHF band. In a series of laboratory tests on the satellite, you put two of those UHF transmitters at opposite ends of the satellite, so that means at a distance 5.18 meters. These broadcast in phase uniformly in all directions. You measure the intensity at points on a circle that is several hundred meters in radius and centered on the satellite. So several hundred meters, much greater than the distance between the sources. You measure angles on this circle relative to a point that lies along the center line of the satellite, that is the perpendicular bisector of a line that extends from one transmitter to the other. At this point on the circle, the measured intensity is 2 watts per meter square. So that will be here the central maximum. So we have this circle here, and at the central maximum, the perpendicular bisector of the center line, we measure a maximum. Part A asks us at how many other angles in the range 0 to 90 degrees is the intensity also 2 watts per meter square, another maximum. Part B, find the four smallest angles in the range 0 to 90 degrees for which the intensity is 2 watts per meter square. And part C, what is the intensity at a point on the circle at an angle of 4.65 degrees from the center line. Okay. So we have basically Young's double slit interference experiment here with a wave frequency 1575.42 megahertz, that's in the UHF band, and we have the wavelength is equal to the speed of light divided by the frequency. The distance between the two sources is 5.18 meters. The constructive interference condition for Young's double slit experiment, remember, is that the path difference is d sine theta, that's equal to integer multiple of wavelengths m lambda. So sine theta is equal to mc divided by fd. So c over f is our wavelength, m lambda over d, which is mc divided by fd. So m can take values 0, plus or minus 1, plus or minus 2. So m equals 0 is our central maximum. Now we're looking for angles in the range 0 to 90 degrees. And that's when we will have sine theta in the range also between 0 and 1. So we will find that mc over fd, our path difference, is going to take values between 0 and 1. Alright, so if I substitute the numbers here, greater than 0 is my m times the speed of light, 3 times 10 to 8, divided by 1575.42 megahertz, so that's 10 to 6 hertz, times distance between the sources, 5.18 meters, will be between 0 and 1. So I will find that m will be between 0 and 27.2. So what are the values m can take? M can take values plus or minus 1, plus or minus 2, plus or minus 27 in this range. Actually for 0 here, we can also put 0, but that's the central maximum. So we're looking for other angles. Other angles correspond to m equals 1. That's the minimum requirement. So I see that I have 54 other angles, 27 on either side of the center line there will be maxima. And because at the center line I have n equals 0 maximum, the intensity will be 2 watts per meter square for these points as well. So there will be 27 on either side of the central line. What are the four smallest angles for which we will observe this constructive interference? Four smallest angles will correspond to m equals 1, 2, 3, and 4. So theta 1, m equals 1, will be sine inverse C divided by FD, so m equals 1. So theta 1 will be sine inverse 3 times 10 to 8 meters per second divided by 1575.42 10 to 6 hertz times 5.18 meters. So this gives me a theta 1 of 2.11 degrees. Theta 2 will be sine inverse m equals 2 now, 2c over fd. So that will give me a theta 2 value of 4.22 degrees. Theta 3 will be sine inverse 3c over fd, which will be 6.33 degrees, and theta 4 will be sine inverse 4c over fd, and this will give me a theta 4 of 8.46 degrees. Okay, and these are basically the symbolic answers and numerical answers. Now in part C, I want an intensity of, I want to find the intensity at a certain angle, 4.65 degrees. Now, what is the intensity distribution in Young's double slit experiment? Intensity is maximum intensity cosine square pi d sine theta over lambda, which is basically equal to the maximum intensity cosine square phase difference phi divided by 2. So that's the phase difference between the two sources. And if you remember, phase difference divided by 2 pi is path difference divided by one wavelength. So path difference is d sine theta. It's 2 pi d sine theta over lambda, but that's divided by 2 becomes pi d sine theta over lambda. So the phase difference is 2 pi d sine theta over lambda, which is basically equal to c over f. So with that, for phase difference divided by 2, we can substitute the numbers here. So phi divided by 2 becomes pi, 2 pi, so that's going to be pi multiplied with 5.18 meters. Now we're looking at an angle of 4.65 degrees divided by 3 times 10 to 8 meters per second, multiplied by the frequency 1575.42 times 10 to 6. So this gives us a phi/2 value of 6.928 radians, and therefore the intensity at this point will be I0, the maximum intensity is 2 watts per meter square, cosine square 6.928 radians. And the corresponding intensity is 1.28 watts per meter square. Okay, so in this problem we're talking about a global positioning system where two sources, two low power transmitters, are at two opposite sides of the satellite separated by a distance 5.18 meters, producing in phase and uniform waves with frequency 1575.42 megahertz. And we're looking at a really far distance. This distance between them is 5 meters, but we're looking at hundreds of meters distance, a circle around this region. So that's basically so that the parallel ray approximation holds. And the parallel ray approximation tells us that the path difference d sine theta is m lambda for constructive interference in Young's double slit experiment. So we see that m equals 0 corresponds to the central maximum, where we have an intensity of 2 watts per meter square. We want to know what other values of m are possible between 0 and 90 degrees, and we find that mc over fd, which is sine theta, should be varying between 0 and 1 when theta varies between 0 and 90 degrees. That gives us, other than 0, 27 positive and 27 negative values for m, 54 other angles, 27 on either side. Four smallest angles will correspond to m equals 1, 2, 3, and 4. And if we substitute the numbers here, we can find where the angular positions of the maxima again, where the intensity is maximum, 2 watts per meter square. The intensity distribution for Young's double slit experiment we know is I0 cosine square phi/2, where phi is the path difference. Path difference divided by 2 pi is phase difference divided by lambda. So path difference is 2 pi d sine theta divided by c over f, which is lambda. So if we substitute the numbers, we find a phi/2 of 6.928 radians, which gives us, using I0 equals 2 watts per meter square, intensity of 1.28 watts per meter square at the specific angle 4.65 degrees.